Good afternoon. Welcome to Drafting and Design Center. As you know that Drafting and Design Center, which is NPA Infracon, provides educational videos for viewing purpose. In today's session, we will go through rigid and flexible pipe. We will talk about the pipe and soil interaction, common modes of pipe failure, loading criteria, and few example to calculate the loading on a pipe within the given embankment condition. So just to let you aware that why we going through today's session is because I was working on a few of the assignment regarding to CCTV investigation for underground network of the council pipes, and I thought of making some loading calculation just to recap and understand myself. And side by I was thinking about why don't I create some presentation on this as well. It might be beneficial for professional as well as studying graduates as well as students in civil engineering. So therefore I have made that short presentation. I hope you will like it. So as you know that the pipe embankment, this is how it looks like. Foundation is the critical part where depends on a given classification and soil condition, geotechnical investigation. Bedding is also a primary criteria. If your foundation is not strong, then it's advisable to have geotextile or some other treatment to make the foundation at least more than 2 to 3 cbr. Bedding is a underneath the pipe. Haunch is indicating the side of the pipe. Spring line is the middle of the pipe, backfill, and then final backfill. So we're gonna calculate the theory of once you have embankment in place for highway loading as well as loading criteria, how much the load of the pipe will take in a given condition of width of the trench, height of the cover, and type of the pipe, and bedding type, and given embankment condition. Usually in roadway, we prefer class 2 to class 3 aggregate compacted in a layer of 150 all the way from bedding to the top. So some other terminology, uh, which is top of the pipe, crown of the pipe, inward of the pipe, bottom of the pipe, and haunch zone. Now, when we do installation of pipe, we can see on a side that trench cross section, and sometimes it is soil. If pipe is about 300, 350 outer dimension, then the trench should not be exceed more than 900 meter wide. And haunch zone is the one we provide proper compaction of bedding all the way to the top as well as haunch zone. When it comes to rigid and flexible pipe, rigid pipe can be concrete all the way to PCC, asbestos, reinforced pipe, stress pipe. Usually on a strict one, we prefer to have RCP pipe, flexible pipe, steel pipe, ductile, PVC, polyethylene, fiberglass pipe. We have used HDPE pipe as a part of a flexible pipe system, which is polyethylene pipe. The difference in a load transfer mechanism is when the load transfer to a rigid pipe, it then go around the circumferential and then load from bearing will come back and the load will distribute within this wall thickness. And based on that reinforced, non-reinforced, the load carrying capacity will be different. Whereas in a flexible pipe, load acting from all the sides and as the load comes up and down it it sort of buckles and as the buckling occurs side support pressurize it and then it neutralizes position. So that's a load difference between two pipe. Soil class, which is class 1 to class 4, is defined here, and we usually go for class 2, which is gravel, class 2 to class 3, and the way of compaction can be evaporation and impact. These are the other embankment condition where you can see class A is a plain or reinforced concrete all the way up. Class B compacted backfill granular material. Class C lightly compacted granular material loose. Class D. Usually in Australia, most of the street time we use class B bedding. Here is a load transferring mechanism. When the load comes, it just create a central prism and side prism and acts the significant load acting not aside but then center prism and then it distribute within the rigid pipe, whereas here flexible pipe side zone is contributing more forces around it rather than central prism. So that just because as soon as the load comes it buckles little bit and that way arching effect creating a lot of loading condition from side. So this is how I was explaining. This prism is acting and the load is transferring all the way in the pipe. That's a rigid flexible pipe. So when the load acts it buckles it from that to that point depending upon loading condition. So that arching effect distribute the load all the way into down. So that's why here you can have a load, less intensified magneticity, whereas here in rigid pipe the load comes in and it transfer by itself sideway, so it's just creating a two pillar here in side zone. So that's mechanism for rigid pipe. That's a load distribution of a flexible pipe. Steel pipe, flexible pipe, vertical deflection, horizontal deflection. You can see that first time, second time, and where as this horizontal deflection occurs, the side branch pushes it, and it neutralizes its positions. So major cause of failure in rigid pipe is inadequate load carrying capacity of the pipe, non-uniform bedding, inappropriate construction methodology, use of rigid jointing material, resulting in a lack of axial flexibility and stability of pipe, thermal deformation, and differential settlement. So usually you will see that they all from non-uniform bearing all the way to differential settlement are contributing factor in terms of construction side of it, whereas load carrying capacity is more defining factor for design office side of it. Flexible pipe is a ring failure, longitudinal fracture, shear, radial tension, cracking, and wall crushing. You can read by yourself. So that's here in a rigid pipe. As the load transfer, it transfer within the load. So when the load comes in, compression zone creating here, opposite tension zone inside, same side compression zone is inside, tension zone is outside. Some of the failure of ductile iron pipe, rigid pipe, which is circumferential crack. Here is a longitudinal splitting of a rigid pipe. Here is a spiral crack. Here is because of bedding condition and loading condition, sagging and hogging, and bale sharing type. Non-reinforced concrete pipe, as you can see here from pipe manufacturing, this is US data. So typical 300 millimeter diameter pipe, which is a 12 inch, has, if you use class 3 as a load, minimum strength is 38 kN per meter. For reinforced concrete pipe class 4, it is 43 kN per meter. Same thing diameter to all the way into 1000 diameter or more, 43 kN per meter. Here is load data from Humes, Australia. So 300 diameter RSAP pipe class 3 is 34 kN per meter, which is a class 3 43 kN per meter, slightly higher in the US standard, whereas here in a class 3 is about 34 kN per meter load carrying capacity. This was measured in a flexible pipe for 21 year 1000 millimeter concrete pipe. As you can see, with a 1.5 about less than 1 year, it takes maximum load of 138 kN per meter. Load propagation for 20 years is sort of up and down, but then it reduces and then increases, reduces, increases. That's a typical graph. This shows that when you have culvert or pipe condition based on a fill, once you have 300 millimeter of fill, you can project this. 80% of load is transferring into the pipe. So most of the time in urban condition, you have a less than 1 feet of cover. That means the pipe investigation is required to make sure that pipe hasn't cracked it or loosen a support. This another graph shows combined H2 H20 highway load, which is 140 kN per meter, 2 axle vehicle, typical of 2 feet cover. It will take about 17 kN per meter of live load for that particular vehicle. So I hope this session you might get something out of loading criteria and how we can use the manufacturing data into the design. I have also created an example which I can show it to you. So the rigid pipe design. Okay, here. So I have two example, load on the pipe 1 and 2, and equations, which is if I scroll from up, basically that just giving you a diagram of how that equation coming in. This graph is once you created modern equations H by BD using this A B C D E, which is the value of A is 0.19 for granular material bedding, sand and gravel. C D E based on your embankment condition. Using this graph you have a CD value. Once you have a CD value, you can use this soil parameter, which kind of embankment it is, unit weight and the K value. Morton equation is used, WC, CD, gamma, BC and BD. And then this is highway loading, and these are the we shown about different type of bedding factor, and then from bedding factor 3H beam requires strength calculation formula here. So I have reference in a calculation how this formula is being used in here. So what is the maximum load on a very rigid pipe in a ditch excavated in sand? The OD is 18 inch, the trench width is 42, and the depth of burial is 88 feet. Unit weight is 100 lb per feet cube. So 18 inch is about 457 millimeter, deep about 2.5 meter, trench width is about 12 meter, and weight is 120 18 kilometer type sand. So once you KU is referring table 2.1, and also from this graph KU 0.16 for sand and gravel. So if your abutment is gravel and sand, 0.165 is KU. H by BD is from here. H is the height and BD is the width of the trench. And this from H by BD we go to graph here. H by BD is 2.28. So that's 2.28 somewhere else, and condition is B. Condition is B somewhere else, and projecting here is about 1.7. Condition 2.28 is somewhere else here, and condition is B. So it's about 2 something CD value of the graph, 1.6, so which is 2.28, and then BD graph B, and then projecting up, so is 1.6, and WD is the equation I defined before, which is here CD, gamma, BC, and BD. So that's CD, gamma, BC to BD, and that's a load on a pipe. So it's about coming to 34 kilometer per meter. So when you have 800 500 dia pipe, 2.5 meter depth, width of the trench, and the embankment is gravel or soil, it will then carry a maximum load of about 34.31 kilometer per meter. So if I go in here, 34 is here, class 3 is okay, but then I should use class 4 pipe. So, and loading 2. So similarly I have used example 2. In that, as you can see, that diameter of pipe is 381, depth is 4.2, trench width is 0.9, and material is sand. So from H by BD, load on a pipe is 37, about 38 km per meter, which is 3 dia pipe, about 4.5 meter depth, will carry about 37.81, and the highway loading for that is from figure, which is double axial loading, uh, which is just bit negligible, and based on a bedding condition B, C, and D, having determined load factor, uh, the appropriate is class B, which we use in Australia, will have about 29 kilometer per meter, which is class B loading, which I explained here is granular backfill all the way compacted class 2 or class 3 aggregate, and compacted all the way in a 150 layer of thick. So in other words, example 2 saying that 300 pipe 4.2 meter deep will have a class B bedding will have a load on pipe is 29. Therefore, using Australian data, class 4 is recommended. So this is how, guys, we can use this spreadsheet and equations. And all I have extracted this data is from book, which is Buried Pipe Design 3rd Edition, AP Moser and Steve Hoffman. So, if you do like to access this spreadsheet with a pipe and presentation, it will be about $80 Australian dollar. And if you do like to contact us, please send us an email at draftinganddesigncenter@gmail.com. Once again, thank you very much, and thank you for watching. I hope this will be beneficial, will create some understanding about selection of pipe for that loading condition of embankment. And stay tuned in. Thank you. Bye now.